Okay, for our second application of the equal opposite parts principle, I call it reds equal black. So what we're going to do here is I've started with a shuffled deck. It truly is shuffled. Doesn't matter what order these cards are in. And so if it's red, I'm going to put it on the left and then place a card below it face down. If it's black, I'm going to put it on the right with one card face down below it. Okay? So we're going to go through and do this for all of the cards in the deck. Okay? Now, you may want to think about, is there anything that we'll know about these bottom down facing piles? So think back to the principle that we just kind of introduced. And is there anything you can conclude by using that principle regarding the composition of reds and blacks in these down facing piles? So kind of ponder that as I do the work of dealing these. Okay, so how would you apply it here? Okay, almost there. A couple more. There we go. Okay, here. So we have two piles in this column. So we have a pile of up-facing red cards, of course, and then a pile of just down-facing cards. We're not sure what's in those cards as far as reds and blacks. And then we have this pile of black cards on the right with a corresponding down-facing pile below it. Is there anything that we know that might be kind of fun to, reveal? Well, it ends up, and it's kind of hard to believe, really, is that the number of red cards here must be equal to the number of black cards here. Okay? So that is not a direct consequence of the principle that we showed you. Because the principle that we showed you is that if you have equal portions of reds and blacks in a packet, divide those in two, then that conclusion follows. There'll be the same number of red in one pile versus black in the other. But the fact is, there's different numbers of cards in these two piles. Okay? So that's not the way in which this principle is or can be applied, actually, because we have more cards here than we have here. Okay? That will not allow us to use that principle. Okay? That principle simply will not apply. Okay? But nonetheless, how can we know? So there's a number of ways that you could actually take advantage of this information. Now we haven't proved it yet, but you could simply just state, believe it or not, you shuffle those in just the right way so that over here the number of red cards will match the number of black cards. I don't know how you did that, but that's got to be a 1 in a million outcome. Okay? Well, in reality, it happens every single time. In fact, why don't we go ahead and just show you that it's actually true, right? We haven't actually shown you. So how many red cards do we have? 2, 3, 4, 5, 6. Okay? There's 6 red cards. I'm going to put it like that so it fits on the paper. So the claim is there's going to be 6 black cards over here. 1, 2, 3, 4, 5, 6. Okay? And that will always happen. Okay? Well, let me show you a proof of this. So we're going to do the following. We already know that the number of cards in this pile and this one must be the same, because that's how we created them. For each red card we set down, we set a face down card down. Okay? The same thing here. For each card dealt here, we have a card down below it. So why don't we say there's n cards in this pile? So we have n red up-facing cards. Well, that means we also have n cards there. We'll just call it n down-facing cards. Now over here, we have a different number of cards. We'll call it m. and they're black up-facing cards. Well, these two piles also have the same number of cards in them. So we can say this one is a pile of M cards, and they're all down-facing. Well, what do we know? We know that the total of all of the cards is 52. So, for example, we can write 2n plus 2m is equal to 52. Well, we can divide both sides of this equation by 2, so we would get n plus m is equal to 26. This is all we really need to know to complete this proof. And then we'll use our equal opposite parts principle. Okay, so how can this one equation help us draw the conclusion that we need to? Namely, that the number of red cards in here is equal to the number of black cards in here. Well, just look. If we take these cards right here, so in your mind's eye, go ahead and add those. We'll do a little plus. Add those to these. So combine all of those. Combine these cards with those cards. In fact, why don't we physically do that? We'll kind of move the cards around. So I'm going to take these N cards and I'm going to move them next to the M cards right here, right? And then I'm going to do a similar thing. I'm going to now take these M cards and put them next to the N red up cards, like this. Okay? Well, what do we know? We know that the sum of these two packets is 26. That's how they were gathered. We know that the sum of cards in these two piles combined will also be 26. So these constitute a perfect division of a deck of cards into two halves right now. Okay? Well, what do we know? So we know that the number of black cards here this is like 26 cards, must be equal to the number of red cards for this second half of the deck. Okay? Well, just look at this. The number of black cards in this half will be completely determined by the number of black cards in here. Right? Because there's no black cards in here. These are all red. So we can say the number of black cards in this packet, because there's none there, must be equal to the number of red cards in this packet, because these are all black. Right? Okay, these don't contribute any red cards. So from there we can conclude that the number of black cards in this packet must indeed match the number of red cards in this packet. And then if you just remember where we got these from, this one came from over here, right? We just do our little reversal here of where we took them from. And so now we can say that the number of red cards here is equal to the number of black cards there. Okay? And we didn't need really any more than two variables to represent what's going on here. And really, in your mind's eye, you could have actually just done that without having to write down anything, really. Because if these two piles are equal, and these two piles are equal, then it's just as I've written here. It's like having N, N, M, M. Well, you can go ahead and take this one with this one, you'll get half the deck. This one with this one, you'll get half the deck. and then you just draw the conclusion that I have. Okay, well, anyway, that is the principle kind of explained for why there would be the same number of red cards in the one pile where you've dealt out one for one a card for each red up-facing card, as the number of black cards in the other pile where you've dealt out one for one a down-facing card for each up-facing black.